Hi folks, we're going to take a look at the solutions to the Unit 2 Lesson 6 homework. So let's take a look at this first question. It says the half-life of strontium-90 is 29 years, and they want us to write a model for the remaining substance with respect to time using base E. So here we assume that radioactive decay is an exponential process. So here, since I'm working with the amount of a substance, I'll use A. So we know that the general structure of the model is going to look like this. So final amount is going to be equal to the initial amount times E to the KT, where K is some constant. We're going to call it here a decay constant because the amount of strontium-90 is decreasing. So what we know is that in 29 years, the initial amount is going to go down by half. So the final amount will just be half of whatever the initial amount is. And then here, start off with a naught. And I can replace t by 29 because it takes 29 years for this to happen. Okay, and because I can divide both sides by a naught and have those reduce, I'm left with an equation that only has k as an unknown. Okay, so since it's in the exponent, I'm going to take the natural log of both sides since I'm working with a base E model. So it's going to be ln of 0.5 is going to be equal to 29k. And so k is ln of 0.5 over 29. And because this is a fairly reasonable expression to write out and put into my calculator, I'm going to leave it as an exact value. So that means that my model is going to look like this. The amount is equal to the initial amount times e to the ln 0.5 over 29. Okay, there's my decay constant times t, which here my input is a time value. All right, so now we'll use this to solve the remaining problem. So it says, how quickly is the amount of strontium-90 decreasing after 20 years if you start with 20 grams? So notice here, they're not asking us how much of the substance is left after 20 years. They want to know how is it changing? What is the rate of change at the 20-year mark? So that means we're not going to be working with the function itself. We're going to be working with the derivative. So in this case here, I'm working with an initial value of 20, and then this k value as we found. And so the first step is to find the derivative of this function with respect to t, because my input variable is t here, not x. And so 20 is just a constant multiplying the function. Just remove it from taking the derivative. So now I'm left with taking the derivative of this function. So this whole exponent is going to be like my u. So what's the derivative of e to the u? It's just e to the u. So e to the ln 0.5 over 29 times t. And now, using the chain rule, I have to now take the derivative of u with respect to t. Remember, this is just some constant multiplying t. So it's the constant times the derivative of t, which is just 1. So I'm just multiplying by the ln of 0.5 over 29. Okay, and now specifically, I want to know the rate of change at the 20-year mark. So I'm just going to take this expression and replace t by 20. So this is where I'm going to be really careful about how I input this into my calculator because there's a lot of stuff going on. Okay, so you probably have one of these. If you notice above my button there, I've got an answer button. So I'm going to use that so I can calculate this whole exponent and then easily input it into my exponential function. Let's see how I can do that. Okay, so here I've got ln of 0.5, and I'm dividing that by 29, and now I'm multiplying it by t, which is 20. Okay, and this now is going to be the input to my exponential function. So I'm going to go the exponential function, and this is where I'm going to use that answer button now. Okay, it just takes my previous answer and inputs it into this new function. Okay, and then from there, I'll multiply that by 20. Then I'll multiply it by ln of 0.5. And then lastly, divide by 29. Okay, and here we get about negative 0.3. Okay, makes sense that it's negative because it's always decreasing. So now essentially what this is saying is at 20 years, okay, the amount is decreasing at a rate of 0.3. Okay, and let's figure out what this is representing. Well, the amount is in grams, so it's going to be 0.3 grams per unit of time, and here we wrote this model using years as our unit of time. Okay, so at that very moment in time, the rate at which the amount of strontium is decreasing, it's decreasing at about a rate of 0.3 grams per year. Okay, so let's take a look now at question 2. So you can read the question in detail, but essentially we're trying to measure global temperature. And the way global surface temperature is given is it's not just given as the actual temperature, it's relative to some average measurement over the years 1951 to 1980. So if it's a positive number, it means you're above that temperature, and if it's a negative number, it means you're below that baseline temperature. Okay? So they want us to create a model, again using base E, and here they're telling us for the temperature measure with respect to 1980. Okay, so here, since we're dealing with temperature, I'll use T as my variable, so T naught E to the KT. Here it seems as though the temperature, as we very well know, is increasing, so I expect that K value, in this case here, to be positive. Okay, so at the beginning in 1980, the measure was 0.35, so that's going to be my initial amount. And then in 2020, which is at the end, our value is 0.97. Okay, and from 1980 to 2020 is 40 years. So it took 40 years for this increase to occur. And here we see that the only unknown I'm left with is the K. Okay, so let's divide both sides by 0.35. And then we're going to take the natural log of both sides to solve for K. So ln of 0.97 over 0.35. And then I'll divide this whole thing by 40. Now, while I certainly could put this in my calculator, it's not too difficult. This is starting to get a little cumbersome. So I think for this one here, I will approximate the K value, but I'm going to keep lots of decimal places to make sure I don't lose too much accuracy here. So let's do ln of 0.97 divided by 0.35, and then all of that divided by 40. Okay, so here I'll stop until I get a 0 there, so I've got 0.25484, and keeping that many decimal places should give me a fair bit of accuracy. Okay, so if I specifically want the model with respect to starting at 1980, okay, my model is going to be T is equal to 0.35, because that's the value at that time, times e to the 0.25484 T. Okay, and see here how that constant is positive. It's a growth constant. Okay, so we've got our model. Now it says, based on your model, how quickly is the surface temperature increasing in 2022? So again, we're looking for a rate of change. And then when would you expect the surface temperature to measure to reach 2 degrees? So in other words, 2 degrees above that baseline temperature. Okay, so let's start with the second question first. I'm going to have to find the derivative, this function. So again, 0.35 is just a constant. Okay, now I'm taking the derivative of e to the u is just e to the u. So e to the 0. Oh, that should be a 0 here. Let's make sure we get that right. I think, if I'm not mistaken, this was 0.025. Just realized I forgot to write it there, and here I was almost going to forget to write it there. 0.025484 times t. Okay, and now I multiply that by the derivative of my u here, so it's just going to end up being that constant 0.025484. Okay, and I specifically want my rate of change at 2022. Okay, and relative to 1980, that's going to be 42 years from 1980. Okay, so that's why my input value here for the time is going to be 42, 2 more than 2020. Okay, and I'm not going to write that all out. I'm just going to input my 42 in there. Okay, so here, since my exponent is much simpler than before, I'm just going to put the whole thing in. So e to the 0.025484 times 42. Okay, and multiply by 0.35. Okay, and then multiply that by that constant times 0.025484. Okay, and it looks like my value is 0.026. Okay, and let's see what this represents as a rate of change. Well, again, my model is with respect to years, and what I'm measuring is a temperature in degrees Celsius. So it's going to be 0.026 degrees Celsius per year. Okay, so according to this model, going from the information we have from 1980 to 2020, this is the conjecture that we would have made for 2022. It'd be interesting now that 22 has passed to see how this compares to the actual increase or rate of increase of the temperature of the Earth. Okay, so now the last thing here, it says, when would you expect the surface temperature to measure, surface temperature measure to reach 2 degrees? Now notice in this last question, there's nothing here about a rate of change. We're looking for the actual time when the temperature reaches 2 degrees. So to solve this last problem, I have to go back to the original model for the temperature. I'm not working with rate of change in that last question. So here in this question, they're giving me the final temperature that you're trying to find. So that's just going to be 2. And so the only thing left in my equation will now be this t in the exponent. Okay, and of course, in order to solve an exponential equation, step number 1 is to isolate that exponential expression. So I've got 2 divided by 0.35. Okay, e to this whole thing. We're going to take natural logarithm on both sides. And now we're going to solve for t by just dividing. Okay, and I won't write it out, but we'll do it on the calculator. Okay, so here we've got natural log of 2 divided by 0.35. Okay, and now we're going to be dividing that by 0.025484. Okay, and it looks like we have about 68.4 years. But remember what that represents. That represents years from our starting value of 1980. So you got to think, add 1980 to that. And of course I multiplied, so 68.4 plus 1980. Let's try that, and we get 2048.4. So that means, okay, it's, at sometime after 2048. Okay, now if you wanted to be more precise, you could calculate 0.4 of 12 to figure out what month in 2049 this would occur, but here this approximation will suffice. Okay, so sometime in 2049 it will reach that 2 degrees above that baseline temperature according to this particular model. Okay, that's it for these questions.